we are now recording. We are on. We're live. So, Newton's second law. How can we use F equals ma? This idea of a net force causing an acceleration to solve these problems. Step one is to draw a free body diagram. Okay, we need to be able to draw a free body diagram. There are two different scenarios when it comes to solving Newton's second law questions. The first one is when there is a non-zero net force. Okay, this is a winning game of tug of war. So this is a game of tug of war. If you have a non-zero net force, that means there must be an acceleration in the direction of that net force. So you're going to get the sum of the forces, or F net, equaling mass times acceleration. Okay. Now, a very, very important difference here. This sum of the forces, okay? The sum of the forces is different for every question. Every single question. You can't just memorize stuff here. It is different, and my screen is frozen. Are you serious right now? Of course it is. There we go. Sorry, I was highlighting some stuff. So if you have like I said, if you have a non-zero net force, you must get an acceleration in the direction, and that net force is going to equal to mass times acceleration. But the sum of the forces is different for every single question. Okay, every question. You need to draw your free body diagram first, and then get the sum of the force equation. Then whatever that is equals mass times acceleration. Okay, always equals mass times acceleration, but this side changes. Okay, it's like different flavors of ice cream. You're always going to get ice cream, but you can have chocolate, you can have vanilla, you can have mint chocolate chip, cookie dough, brownie, whatever it is. Then this is going to change, but you're always going to end up with a cone of ice cream. Okay, so that's option number one. You get a net force, you get an acceleration. Option number two kind of has two parts to it. The object is not accelerating because your sum of the forces, or your net force, is equal to zero. If your acceleration is equal to zero, then that means that F equals ma, is just zero, not a. Your force is zero. The big thing here to realize is that does not mean the object is not moving. Okay, it could be not moving, could definitely be at rest. That would not give an acceleration, but it might also be moving at a constant velocity. And this constant velocity is a key word to watch for. Okay, to look out for. If you read in a question constant velocity, that's telling you straight up that the sum of the forces is equal to zero. Okay, keyword. If it tells you it's at rest, fine, zero, that makes sense. But if it's constant velocity, that tells you that your acceleration is equal to zero, which means the sum of the forces is also equal to zero. Okay. Now, the other thing about this, which you're not going to see too much, is that an object can be at rest in the vertical direction while still accelerating in the horizontal x direction. That happens in virtually every single question. You will get an acceleration in the x direction, but in your y direction, it's going to be zero because your object is not moving vertically. Okay? If you think about pulling a box along the table, here's a box pulling up like this. Okay, yes, this thing is going to move to the right. What it's not going to do, it's not going to fly. It's just not. Unless you're pulling it straight up, it's not going to fly. It's just going to move to the right and slide across the table. And since it's not going to fly, the sum of the forces in the y direction, that's zero. Okay, but in the sum of the forces in the x direction is going to be equal to our mass times acceleration. Okay, so How do we solve these? These are some problem solving steps. These are not your end all be all steps, but this is kind of the general steps that you should follow to solve every single question. First one, draw a picture, okay? Pictures are fun, they're helpful, okay? Be fun. Don't be like me. Be fun. Draw the fun pictures, okay? Then you can draw your free body diagram for each object. We're only going to deal with one object this year. Put all forces, label it well, make sure you use your coordinate system, so knowing which way is positive and negative. You must do this one. You must draw a free body diagram. That is not an optional step. You have to do that, okay? If you don't do that, I don't even want to look at your paper because it's nonsense. You need that free body diagram. Break up any force vectors, right, into its components. Fantastic. Vector components. We're fantastic at that. You might need some different equations, okay? We're going to see this a little bit later, okay? This will be later, this will make sense, okay? But you might be using forces like the force of friction that has a different equation, so you might need to pull that in, okay? Now we need to apply our sum of the forces to both the directions, right? To get your two different equations, sum of the force x, sum of the force y, just like we were doing with free body diagrams. And now you are just solving the equations. You should end up with a nice equation that you can solve, okay? At this point, you should be able to solve, either sum of the force in the x direction or sum of the force in the y direction, okay? If you didn't, you might need to do a little bit of kinematics sprinkled in there, but you should be able to solve it. Now, these steps I realize are just a lot of words, so let's walk through an example or two to really help you understand what's going on here, okay? So a physics student has a mystery box. Gotta love a good mystery box. It has a mass of 10 kilograms. So we want to first figure out what is the normal force exerted on it by the table. So first step, free body diagram. There's our box. It's beautiful, okay? Forces. Always a force of gravity going down, contact force, normal force going up. Cool. Nothing in the x direction, nobody's pulling it, nothing like that. Okay, so all we can say here is that the sum of the forces in the y direction is just going to be Fn minus Fg. Okay, now an important thing to realize, this box is not moving vertically at all. It's not flying. It's not going up, okay? And since it's not moving up, we can say that the sum of forces in the y direction is going to equal 0 because there is no net force in the y direction. There's nothing that's going to cause this force, this box, to go upwards. So what we can do now is we can say, okay, well, Fn minus Fg must equal 0 because this right here is the sum of the forces in the y direction, and this is mass times acceleration with an acceleration of 0, okay? This looks like a nice equation we can solve. We're looking for our normal force, so Fn is equal to Fg. We know what Fg is. It's mg, mass times gravity, always, always, always. So our normal force is mass times gravity, which is 10 times 9.81, which means our normal force is 98.1 newtons. We just did our first dynamics question. Yay! Okay, started with a free body diagram, came up with our sum of the force equation, figured it out that it's not moving, so it's equal to 0, so we can solve it. We were looking for our normal force, set it equal to Fg. We know Fg is always, 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 that's important to notice, right? Our Fg is always mg. Doesn't matter what's going on, your force of gravity is always mg, okay? Your normal force is not always mg, okay? And we're gonna see that Fn is not always Fg, but Fg is always mg, okay? Awesome. So a chemistry student wants to open it because those sneaky chemistry students always want to know what's going on. So they are going to push down on the top of the box with a force of 40 newtons. What is the normal force now? How much contact is there between the force and the box? Do you think it's going to get bigger or smaller if somebody is pushing down on it? Probably bigger. So first step, draw a free body diagram, okay? Always, 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 force of gravity. There's contact here. So we've got our normal force. If we are pushing down, that means we have an applied force going down like this. That applied force is 40 newtons, okay? Next step, sum of the force equation. Sum of the forces in the y direction, Fn minus Fg minus Fa. Okay, cool. Very similar to the last question, but we just added in an extra applied force. The sum of the forces in the y direction is still equals to 0 because it's not moving, right? If you have somebody pushing down on a box, it's not going to magically start flying up. So what does that tell us? That tells us that Fn minus Fg minus Fa is all equal to 0, which we can take over here. We're looking for our normal force. There's our normal force, Fg plus Fa, because I brought both of these terms, added Fa, added Fg to the other side, okay? Good thing we know a lot about these terms. We have mg plus 40 because there's our applied force, which means we already know what our normal force or what Fg was, right? That's our 10 newtons times 98.1, sorry, not 98.1, 9.81 plus 40, which means our normal force is going to equal 138.1 newtons. Fantastic. So much fun. Are you seeing the pattern here a little bit, maybe? Hopefully. Okay. So let's take this a step further. Now this chemistry nerd's trying to steal it, so they're pulling this box upwards with 40 newtons. Okay, so they're pulling it straight up. Now what's the normal force? So this one is going to be yours. Okay, I'll do that. It's very, very similar to this, except now this applied force is going upwards instead. Okay, see if you can do that one. Okay, just for a fun fact, just to tell you, the answer is 58.1 newtons. Okay, the normal force is decreasing because they're pulling it up, but since there's still a normal force, it's still not moving. Okay, we're going to do this part D together. After the chemistry student gives up, the biology student wants to steal it, so they pull upwards with a force of 120 newtons. What happens to the box? Okay, in order to know what happens to the box, let's find Fn. Okay, so here's our box. I'll do this in black. There we go. Oh my goodness, why are you not working, iPad? There we go. So we've got our force of gravity going down. We've got our normal force going up. We've got our applied force, which is now equal to 120 newtons going upwards. So the sum of the forces in the y direction is going to be Fn plus Fa minus Fg. Okay. Now, what we're going to do is assume that the acceleration is still 0. We're going to assume there's nothing happening to this box. So we're going to assume that the sum of the forces in the y direction is equal to 0. We're not told that. This person's pulling up with quite a bit of force, so we don't know what's going to happen, but we're going to assume it. So that tells us that the normal force plus, not the force of gravity, plus the applied force minus the force of gravity equals 0. So this normal force is going to be mg minus our applied force, which is going to be 98.1 minus 120, which means our normal force is negative 21.9 newtons. Oh, geez. Oh, geez. This negative. A negative Fn equals bad news. If you have a negative contact force, that means two things. You're either not in contact anymore or you fell through the object, okay? Because if you don't have a contact force, you don't have contact anymore. Negative like that, it just doesn't work, okay? So what this is telling us is that we assumed wrong, right? We assumed wrong, and that this box actually does lift off the table. Okay, that biology student was strong enough to pull the box off the table. And if we think back to the very first question we did, where we figured out if this box is just sitting on the table, no problem, it has a normal force, it has a weight of 98.1 newtons. So this thing takes 98.1 newtons for it to move vertically. This biology student's pulling with 120 newtons, bigger than 98. If they're pulling with more than it takes, you're going to get some left over. It's like paying for food. If you give them too much, or paying for anything, if you give them too much money, they give you change, right? That change is your acceleration. Okay? Super fun. Any questions? How are we feeling right now? I'm going to set up a poll. I want to know how you're feeling. So how do you feel? Not so much. So this says these types of questions. Think of it more of as just like this unit so far. Like, how are you feeling about everything that we've done today? Where are your feelings? Do 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 do. Got a couple more people, maybe they fell asleep at their computer. Understandable. Okay. If you haven't answered yet, I'll give you 10 more seconds. 10 more seconds to answer. Okay. Okay, so it seems like most people are with me, so that is good. It is kind of, these are confusing questions. But the really, really nice thing about this unit is that all the questions are virtually exactly the same. So as we go further and further on in this unit, you're just going to get more and more practice with this stuff, which is really, really nice. Okay. Now, we're going to do a little bit more. What do we have? This question number 4, we're not going to do. And then question number 5, I'll do on YouTube. Okay. So we're going to do this last question together and then we'll call her a day. So everything we just did in question number 1, all of that was in the vertical direction. Oh, it is frozen. Thank you. There we go. So everything we did in this question number 1, was all vertical direction. We had no horizontal movement at all. All of these are all many different options, pushing up, pushing down. Your normal force changes, right? The big thing to take away from this section was that your normal force changes. The normal force changes. One thing that I see students struggle with all the time is that they assume that your normal force is always the force of gravity because you always have this pair. It's just not true. Okay, your normal force changes. You need to find it for every single question if the question asks you. Okay, you can't just assume that it's FG. So let's add an X direction in now. Let's get some movement side to side. Okay, so now a math student comes along. Gross. And they want to try to steal that mystery box. Okay, so they tie a rope to one side of the box and they pull with 40 newtons at an angle of 30 degrees to the horizontal. So we want to draw a free body diagram, figure out what the normal force is, and then find the acceleration of the box. Okay, so if you need help picturing what's going on, by all means, draw a picture. Okay, that's what's going on. They're being sneaky. Okay, they're pulling this way. I don't love putting forces on stuff like this. Okay, oh yeah, wait, we also know 30 degrees. Okay, I don't love putting forces on here because it gets messy. Okay, these pictures are more for your benefit and to see, okay, oh yeah, now we've got a box, someone pulling it. Cool, there's our gross math student. Cool. So we can take this and we can simplify things a lot nicer by making our box like so. Okay. You can put your dotted, I'm going to call this tension, which is just my applied force. They're the same thing. Okay. I like using tension better than applied force because I like TX better than FAX. That's just a little personal preference. I like one subscript rather than two. So I like using T. Okay. So we know that's happening. We know this box is sitting on the ground. So we know that there is the force of gravity going down. We know that there is the normal force going up. Okay. We don't like this, right? We don't like angles. We need to do something about this. Okay. We know that this thing is acting at 30 degrees, which means we can break it up into a TX component and a TY component, going like so. Okay. Now, this triangle, right, this force, I'll do it over here. Okay. This is what we have. 30 degrees. There's our tension, which we know is 40 degrees. Okay. There is our TX, and there's our ty. That looks like it's part of that. I'm going to move it over here, right? That's all we have. This is just, we've taken our triangle, our vector component triangle, and we've just broken it up into our x component and our y component. That's it. So if we're pretty good at trigonometry right now. So we know that tx is going to be 40 times the cos of 30 degrees. And we could even go a step further and actually find that. That's going to be 34.6. And we know that ty is going to be 40 times the sine of 30 degrees, which is going to be 20 newtons. Okay. We know both of those things. That's cool. If this reminds you of vectors, that's because it is. That's all this is, vectors. Okay, so we know our x and y components. That's great. It's an extra step when you are pulling at an angle. So that's our free body diagram. Okay, this right here is beautiful. Okay, cool. Now, what's the normal force on the box? Okay, from this free body diagram, okay, we need our net force equations. So since we are looking at the normal force, all we care about is the sum of the forces in the y direction. The normal force doesn't exist in the x direction, so we don't care about it. So if we look at the sum of the forces in the y direction, we have our Fn going up, we have our Ty going up, and we are fighting against the force of gravity going down. Okay, and we can take this whole thing and we can say that Fn plus Ty minus Fg all equals to 0, because we assume, right, just like always, we assume that the sum of the forces in the y direction is equal to 0, and the box is still on the table. Trust the math. Remember in the last question that we did, we got a negative normal force, okay? Trust the math. The math will tell you if you're wrong. Don't be afraid. Make this assumption virtually every single time. Unless the box is telling you straight up it's moving vertically, assume that it's not, okay? The math will tell you otherwise. So we're looking for the normal force, okay? So the normal force is just going to be Fg minus our Ty. Well, what the heck is Fg? That's mg. Well, what the heck is the mass? The mass is still 10 kilograms. Gravity is still 9.81. Our y component, we already figured that out. That's 20 newtons. So we can go ahead and say that this normal force is a good old 78.1 newtons. There we go. Virtually identical to the question that we did over, I don't know where it is. Virtually identical to this question, except it's virtually identical to this question, except our applied force in part D was big, which gave us a gross normal force. In this case, our applied force, the y component is only 20. So it's not big enough to make it anything happen, so it's still on the ground, okay? So to get from here to here, remember, we're just doing algebra. We're just taking this, we're adding Fy, and we're subtracting Ty. We're just doing algebra to move it over to the other side, okay? Now that we've found our normal force, we can go to part C. What is the acceleration in the of the box, okay? The acceleration we assume, okay, this acceleration is going to be in the x direction, okay? So all we care about, I don't want to do that in orange. All we care about now is the sum of the forces in the x direction. All that's happening here is just our x component. That's it. There's nothing else happening, okay? But we know always that the sum of the forces in the x direction is going to be mass times acceleration, okay? Now, technically, if we want to be super proper, we would put an x component there, okay? And we would just specify that ax is the x direction acceleration, okay? But I'm not gonna lie, it's kind of gross, right? We're only ever gonna have one acceleration. You're not gonna be accelerating in both the x and the y. So just ignore it, okay? Just leave it out. Don't do it. If you're talking about an acceleration, you know, because of this x value, you know that that's your acceleration in the x direction anyways, okay? So just leave it out, okay? Don't do it. But technically, if we wanted to be super correct, that's what we would do. But we combine those two to tell us that Tx is equal to mass times acceleration. We know our Tx, we know our mass. We're looking for acceleration, Tx divided by mass. So acceleration, which was 34.6 divided by 10 kilograms, which means we have an acceleration of 3.46 meters per second squared in the x direction. Cool. That's it. Okay. The only thing that's going to get complicated with these questions is we're just going to add more pieces. We're going to add friction. We're going to put things on a ramp. We're going to do more stuff like that. So we're just going to have more forces. This is a relatively simple example because there's some of the forces in the x direction is just one little measly thing, right? We're just going to add to it. That's it. But this is the general process. Free body diagram, sum of the force in the y and x direction, solve for the normal force if you need to. In this case, the question asks for it, but you don't always need to solve for it, and then find your x direction. Awesome. Awesome, awesome, awesome. This question number 4, okay, this is just for fun. You can follow along if you want. This is a multi-mass question, 2 children being tied by a cord being pulled together. So we've got two different masses, 2 different free body diagrams, 2 different equations, and this gets us 2 equations, 2 unknowns, a nice system of equation that we can solve. I'm follow along, you know how to do everything here. I'm not gonna ask you questions like this, okay? So don't worry about this stuff. What I do want you to worry about is this, okay? I want you to try this one on your own. I will put a YouTube video on how to do this question, but I want you to try this, okay? This one, I give you a big hint, kinematics, okay? Kinematics meets dynamics because dynamics gives you the acceleration. Acceleration is everything we were just doing in kinematics. Oh my goodness. So if we want to know how we're going to move this hay bale 100 meters in 40 seconds, oh my goodness, we can use that to maybe find an acceleration. And then if we find our acceleration, we can work backwards in dynamics and find forces. Ah! It's so exciting. So exciting. Okay? Whew. I'm sweating now. That was good.